Hello. I think in a long time you're going to get some tutorial class without a break. Yeah? Where are you right now? Yeah, but 7th must have started. No? How many classes? Yeah, so I think this week you should finish up 7 and maybe you might have a quiz next week. So let's wrap up 7 from our side. I will not be in Thursday and Saturday. So I'll come back next Tuesday to start chapter 8. So nothing, we have very less amount remaining. I've already done the Carnot Cycle, yes? So just few questions. There's again, they bring about the reversibility and the irreversibility. We have already talked about this. What's the take home? Like if I ask you conceptual questions, when does the system become irreversible? And give me 2 examples. I don't want essays. Nobody is going to write essays. Nobody is going to read the essays. Firstly, you can write all you want. Nobody is going to read it. When does the system become irreversible? Just in 1 sentence you answer this. Sufficient. Everybody has used a rubber band. Everybody has used sweatbands, headbands. A lot of sporting equipments have a lot of elastic materials. All of you use products on a regular basis. The shoe soles, initially it feels a certain way, then after a few months it feels something else. So why am I answering the question? I thought I already answered the question. When does a system become irreversible? I thought I just answered the question. Yes? 2 marks. So that you cannot write more than 1 sentence. Otherwise I'll put it for 1 mark. And some of you write long essays for 1 mark, by the way. And you waste your time. Yes, question still stands. Answer the question, we'll move next. Otherwise I'll be stuck with it right now. Ask a simple question. I hope you understand what is reversible. What is reversible? Being able to what? So is the elastic material reversible? Have a doubt? Sure? Very sure? Even if heat is dissipated from elastic material, it's reversible? You take a rubber band and you go, don't do this experiment and keep it on your lips, it'll burn. So don't burn your lips, just saying. So what's going on there? But the material is reversible and elastic, but does that make that process reversible? No. So then what's the answer to the question? When is a process irreversible? When something permanent changes either in blah 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 and blah blah blah. Which are the 2 blah blah blahs? When something permanent changes either in dash and dash. What are those 2 dashes? Material or surroundings. That's it. That's it. Permanently, if it changes, you cannot put it back. If there's something that you cannot replace and put it back, it's irreversible. If you can put it back, then it's reversible. So when you have this rubber band going, tension, compression, tension back, I didn't say compression, I'm not pressing. Just loading, unloading, loading, unloading, loading, unloading. heat starts to get dissipated because of internal friction, and that is gained by who? Now, can you catch that and put it back into the material? Huh? Okay. So there you go. As long as you devise an experiment and catch it and put it back into the material fully. So give me another example. Now don't start using the same example and say automobile tires. Obviously it's the same example. Nobody can catch that heat on the road and put it back into your tire. Give me another example. Irreversible. So there is some load on your gas. You remove that load, it will push up. Yes? It will push the piston up. So it did work, yes? Now you want to compress it. Will it be the same kind of work? If it's different, then that's irreversible. So this going up work is a expansion work, tension work, tension. It's getting tense, you're pulling it away from each other. The reverse work is compression. So many of the materials do not exhibit the same behavior in tension and compression. In tension, I have to talk in molecular scales only. They will streamline and they will shear and they will move away from each other in tension. But when you compress it, now you are trying to force them and bring them close to each other, for which they do not like to, and they behave in a more incompressible manner. So like as though there is hydrostatic pressure, that, you know what is hydrostatic pressure? Pressure in all directions. Like suddenly it behaves like very isotropic. So then the resistance will be higher. You will have trouble compressing the same material. But you stretch it, it will streamline and it will do the work. You try to force it and compress it, the same material will appear different. So is that a reversible process if I do tension compression to be the same? Is it the same? Louder? No, obviously no. But both are doing work. In both cases you are trying to do work. Another example. Charging mobile, even in a reversible battery. Oh, okay, why? So the polarization is not reversible of the charges in your material. So you know what charging is. You're binding the charges and getting them to polarize. Polarize, it's a battery. Battery holds charges, got it? And then you reverse the potential, they will dissipate the charges and give you current. Got it? Battery, working of a battery. Very good example. It's just like tension and compression. Very good, you use that analogy. Also there will be losses. There will be heat loss. That also you cannot catch and put it back in your material. Obviously you cannot. Friction. Friction is going to be one major irreversible thing. Gas going into vacuum, make it reversible. You have to push it back and you have to compress it and also remove the heat. Not only do the work, you also have to remove the heat. Irreversible. The vacuum out and reverses irreversible. So can you write friction, vacuum expansion, which is like there's nothing, no resistance there. It just expands by itself. Friction, expanding by itself without a resistance. Zero resistance expansion. What else did you say? Hysteresis. What I gave you the example of a rubber band and tires and charging and recharging of a battery is hysteresis. It develops an hysteresis. An elastic material, a rubber band which is elastic, slowly appears to become viscous, less elastic. That is what you say, right? The rubber bands become less elastic. It has become more viscous. So it's dissipating more and more heat because of the usage as you go with number of cycles. So it carries a baggage that each cycle is now dependent on the previous cycle. That is the hysteresis. It has a memory. It carries the previous memory. And it becomes bigger and bigger. Hysteresis becomes bigger and bigger. What else? Something else I told. Yeah, okay, vacuum is over. What else? How about just heat transfer from hot to cold? Can you make it reversible? Just say no. Yeah, you have to do work to make it reversible. Refrigeration. So refrigeration is not a reversible process. Hot to cold is easy, but from one location, if you have to make it colder, you have to do work. Write it. Refrigeration. What else? Mixing sugar and water. Can you reverse it? Can you? No. Dropping a ball on the ground. Can you reverse it? The ground's got to do whatever it has to push it up. Can you? You can if you are very creative. You have to heat the ground and then you have to orient and do all that thing. Yeah? You have to put a lot of resistance and heat the ground and make the ball go. Like in Marvel comics. You have to be Stan Lee. Ball dropping on the ground is not reversible. Eventually it will fall off. Everything, energy is dampened. It's all converted into friction. It loses elasticity after 4 bounces. Yes? Okay. Mixing sugar and water, you cannot demix it. If you demix it, you have to do work. Got it? It's not spontaneous. If you just put sugar and water, it will intermix. If you want to demix it, you have to do work. You have to do work. Got it? So whenever you have to change the input, it's irreversible. So then, my question is, even in these tough examples of irreversible processes, how to little bit make it reversible? So that at least temporarily it might appear reversible, temporarily. Obviously, all these examples are straight up irreversible processes. So take the case of elastic rubber band. How to little bit make it reversible? You have to be very less amount of increase and slow rate of increase. So the stimulus should change in small amounts and in slower rates. The rate of change also should be slow. Then you will have a reversible process. So if you go little slowly, you have to give time. If you give time for equilibration to happen between little change of state and the previous state, then it will be reversible. Because now it can go either way. You have to develop some kind of a quasi-equilibrium during the process. So which means you have to chew slowly when you are eating the food. So there is an equilibrium between unchewed food and chewed food in your mouth. Yeah? Slow. Slow bites, small bites. Slow biting, small bites. Then you have an equilibrium. I think you can attempt that by keeping a nice candy or something and you bite very slowly. You cannot tell whether you bit or whether you did not bite. There is an equilibrium. Yes? You cannot tell. You cannot tell. Infinitesimal change of the stimulus and slow rate of change. That will maintain an equilibrium. So that's what I have between reversible and irreversible process. Any other questions? To be quasi-equilibrium. There's a small change in the orbit. Obviously. Gravitational field is changing. Changing all the time. The permittivity of vacuum is changing all the time. Epsilon 0. G is changing all the time. So, but changing very slowly. Some constants that you have in science keep changing over time. Yes? They're changing. G is changed. Epsilon 0 is changed. Some other universal constants are there. I think the nuclear force constant is changing. Any other questions? So you have to be very slow, reversible process. That's the beauty of it. Slow and small. Small amounts. So you won't be able to tell whether you are going up or down. That's basically what is equilibrium. You maintain a temporary stalemate. Got it? Stalemate. So when you lift weights, what does the guy tell you? Does he tell you, go for it? That's the whole point. I don't think you need a better example than going to the gym. Go to the gym, hit the gym. Lift some weights. Yeah? Tell me, come back and tell me whether you do it quasi-equilibrium or whether you do it in irreversible process. Yes? Small amounts, slow rate of increase. So you know that irreversibly structure does not change in your body or in the surroundings. So you should not hurt yourself. How do you prevent yourself from getting hurt? Slow and gradual. So in the previous class we spoke about the viscosity of the material changing, the working fluid of the viscosity of the material. If it changes in the refrigerant, you are gone. You are dead. Your number of cycles will decrease and the amount of work that you are putting in will start to increase. The efficiency of the refrigeration will go down. The structure of the working fluid and the viscosity of the working fluid should never change over cycles. So if it becomes irreversible, you are finished, you are done. So in the batteries also, that electrolyte should be like how it was from day one. Now the electrolyte should not get contaminated and it should not lose its charges and all that. Then the transfer of the ions will go down and then you will not get the current out of your battery. Yes? Then what does that guy do? He says it's time for you to replace your electrolyte. And it should not be consumed, the amount should not change, all those kind of things. So combustion, pyrolysis, vaporization, phase changes, structural changes, all this should not happen. If these things happen, it's irreversible in the material. Okay, moving on. Write the Carnot cycle. We'll do the Carnot cycle and end chapter 7. Oh, by the way, one more thing. All of you know that, I think in the tutorial they would have told you, you don't have to write QH, QL. Instead of that, you can write TH, TL. You can represent the heat by temperatures. Why is that? Because the heat is measured with respect to change in temperature. So change in temperature from a common reference. What is that common reference? What is that common reference? I'll give you a hint. You have to assume like it is ideal gas. So what is the common reference temperature point, scale, temperature point? Common reference temperature for ideal gas? At which pressure? At very high pressures or at very, very, very low pressures? Extremely low. So basically zero pressure. Zero pressure. So because the change in heat is change in dT, so you will change it with respect to the same reference point. You can represent Q's by T's, just by T's. temperature of the hot location. So what they're doing is, it's a very simplified version. It's actually not fully real world. So you're eliminating the material and you're simply saying it is dependent on the temperature of the hot junction and temperature of the cold junction. But that is not the case, right? If you use two refrigerants of different materials, so what if the junctions are the same? Will you still get the same? No, you won't. It's dependent on the material. But here you are assuming sort of you get rid of the material, no impact of the material. You assume it is like a ideal gas material. So one time, just for your benefit, can you write in terms of Q and T's? First one, heat engine. Heat engine, output by input. What's the input? What's the input? This is heat engine. I did not say heat pump. Heat engine. What's the output? No, what's the, what's the input? Heat. What do you get? Work. So you can write this as TH minus TL. Okay, go to the next one, refrigeration. COP. You write it by yourself, COP. What is the output? QL. I need heat to be removed at the low temperature junction. For that I have to do work, compression work, QH minus QL. So COP for refrigerant is TL divided by TH minus TL. Heat pump, you have to give the heat at the hot location. So the output is QH. So COP for a heat pump is TH divided by TH minus TL. Clear? So don't blink there, don't look for Q's. They may just give you T's. Use the T's. And I think it's better if you use in Kelvin, or you check with your tutors. What will happen if you use in Kelvin and what will happen if you use in, will it make a difference? Obviously it will make a difference, yes? Okay, don't make mistakes now. You should use in Kelvin. It will make a difference if you use Celsius. Yeah. You know, efficiency of heat engine cannot go beyond 1. Okay, so don't start writing 3, 4. COP can go up to infinity. So there you will get caught because you might get an answer like 35 and you may not know whether it's right or wrong. But for a heat engine, if you get 35, you know you're wrong. Yes? Okay. At least you should know where you're right and where you're wrong. COP you won't be able to tell. It can go to whatever number it wants. Write the Carnot cycle. I've already done this. You write it. Then I will write. PV. I don't want a PT. PT is also fine. We have done PT also. You write PV. PV. I like to start from compression. If you like to start from evaporation, be my guest. You can start with isothermal evaporation and then it will do work on a turbine. So that is adiabatic expansion. Isothermal expansion is your first step in the boiler, evaporated. Now that is hot and it is under high pressure. So it will do work on the turbine and it will expand. That would be adiabatic. So after it does work, it is tired now. You need that fluid back again. You need to use it back again. Yes? So what do? You have to condense it. You have to condense it. Isothermal condensation. Back to a condenser. And then you have to again give it pressure and get it ready for the next cycle. You have adiabatic compressor. Can you write it? I've already done this. Write it again. I not only did Carnot, we also talked about why volume changes more in isothermal condition and why volume changes less in adiabatic condition. All done, over. Go watch that video. Now I'm just doing this just to write the equation so that you're all set for your tutorial and have a good tutorial, 7 chapters. I'll catch you chapter 8 next week, next Tuesday. I may do 1 special class. If I feel like it, maybe 2. Most probably only 1. Don't worry, in the end, I will do a special class in the end. I'll tell you in advance. Okay, let me write PV. PV. Help me out. So since you guys like to go evaporator first, isothermal expansion. So the volume changes by lot? Yes? Or volume changes less? Whole class gone. You got to go watch the video. Volume changes lot or less? Huh? I thought I already used the ammonia example that day. 500 times the volume change is all done. Does it change lots or less? Louder. Lots. The pressure will change less. So number it 1, 2, put your arrows, write iso expansion, phase change. This is phase changes from L to V, liquid to vapor. What is the appliance that you use? You see, I'm like a broken record player. What is the appliance you use? Evaporator, boiler. And this is isothermal. Next, it goes into turbine. You have adiabatic expansion in the turbine. It's more oriented. The volume will change by less, but the pressure will decrease more. 2 to 3. So it's adiabatic. So there is no pumping of heat or removal of heat from the surroundings. So when it expansion, when it does work, it will cool off. So it will go from hot location to cold location. That's how the temperature is changing. This is a TH, correct? It will go to TL. When it hits step 3, it has cooled off because it's adiabatic. You're not pumping heat continuously. So it expands, it loses heat. If you compress it, friction will develop and it will generate heat. So this is the opposite of it. It will lose heat. It will go from hot temperature to cold temperature, TL. What's the appliance? Turbine. Okay, next, isothermal condensation. Volume will change by lot? Yes. Okay, 3 to 4, arrow. So again write isothermal condensation or compression, you write compression. Better because you're writing expansion, you write compression. Make sure you label this temperature here, TL. This is TL. So now you have to again give it pressure and get it ready for doing work. So you have to compress it again. Adiabatic compression. So what happens adiabatic? It's insulated. So when you compress it, there will be friction inside. The temperature of that material will increase. It will go from TL to TH. And you are back to 1. 1, 2, 3, 4. Write it however you like to write it by yourself. That's it. There's nothing complicated about this. So in all the steps, work is being done? Yes or no? Huh? Okay, 1 mark again because I want to clarify. Why work is being done? Okay, louder. Volume is changing, so work is being done. How will I determine individually the work for all the 4 steps? Area under those steps only under those steps. So what you should do is you put dotted lines like this right now. And you can do your shading however you want. Be creative and do the shading. So for 1, 2, it is the area under the curve just between the vertical lines that you have. 1, 2. 2, 3 is between 2 and 3. 3, 4 is between 3 and 4. Clear? The area under the curve, very good. So you can do it geometrically also. You can literally experimentally determine this curve and you can measure the area under the curve by hand. You don't need equations, you can do it graphically. But you need to get the points accurately, yes? So in which case the work looks more? In the iso case or the adiabatic case? You cannot tell because how you can tell? You don't know the PDV, both P is changing and V is also changing. Until you do the area under the curve, you cannot tell, correct? You cannot just go by the volume thing. You cannot just go by the volume change. It's like your piston, both pressure is also changing and volume is also changing. So you don't know what the work done until you really do the area under the curve. You cannot make a guess, correct? Yes? But do some numericals, then maybe you will get some numbers. Then you can sit and look at the numbers. Is the iso case W more or is the adiabatic case W more? That's why you have to do numericals. Do it. Okay, what equations do we use here now? So go back to your first law of thermodynamics. Write down your first law of thermodynamics. What is it? Help me out. I have no idea what it is. What is first law of thermodynamics? The money balance that I have is equal to how much money I received and how much shopping I did. Yes? Okay. So state function, path function. Yeah? W is positive work done. So reverse it back, dou Q is equal to du plus dou W. So du is, how do I represent du with temperature changes? Cv dt. Cv dt. Work is PdV. Ideal gas, if you take ideal gas, work is PdV. Then can I make it into ln V? P ln V. Am I right? Or should I put RT or something? Yeah, I should. Work for ideal gas. What should I do? So dou W equals RT ln V. Is that right? Is that right? RT ln V. You should know better. It's all old chapters. Correct? Is that right? Okay. So don't trip over this, yeah? So in the numericals, if the work is being done, then you use Cv dt. They have to give you the constant volume heat capacity of the material. And specific volumes you can find from the table. So importantly, in a Carnot numericals, what do you need? You need temperatures of the hot location and the cold location. Okay, before we wrap it up, now in the first step of isothermal expansion, is that correct? 1 to 2 is isothermal expansion. So what would be the equation? Heat is being supplied or no? Just tell me that. I've come back here. Heat is being supplied or no? Huh? It's isothermal. Heat is being supplied or not? Louder. Okay. What happens to du? Oh, why? So you just put du as Cv dt and you put it 0. I'll come back to it, yeah? I'll come back to that. So work is there. Is it doing work? Okay. Now quickly, since your mind is fresh on the internal energy and you said change in, but it's changing from solid to liquid to vapor. Why is U not changing? You remember in the class when you sat one day, I came to Parmeshwaran's tutorial, I asked a question, how many ways you can change U? Remember the question? By phase change, will the U change? Obviously it will change. Now why are you putting 0 here? 25 marks for this question. Answer this question. Why 25 marks? Let's put 75 marks. No, why 75? Let's make the final exam with this question. Entire 100 marks is for that question. Obviously, liquid is becoming vapor. How you can tell U is not changing? Good question. Ask the tutors this question and come back and tell me what happened. Everybody should go to your tutorial class and ask this question. Clear? No simply writing CVDT and saying it's isothermal and just putting 0 there and making U 0. Because I am thinking liquid is becoming vapor. How U can be 0? How change in internal energy can be 0? Good question. You should ask this question to yourself. So nicely you said du is 0. You are the guy who was there in the tutorial also. Okay. Everybody understand the question? Yes? How, when a liquid is becoming a vapor, you claim that internal energy does not change? So it's like telling in an isothermal case, if chemical reaction is happening, then U won't change, U will change. Because the reactant is becoming product. Obviously U will change. So it's just like that, like reactant product only. Reactant is initially liquid, it's becoming vapor. Or the other way, vapor is becoming liquid, U will change. Or if I did like changing pressure, even if it's isothermal, will U not change? Obviously it will change. Because it will expand, got it? Isothermal expand, I can change pressure and I can make U change. That was the question I asked in the class. What are the few ways you can change U? Not this class, in the tutorial I asked. What are the few ways you can change in isothermal conditions? Correct. So you cannot put CVDT and just put 1 0 there and take off. Because obviously I don't understand, neither do you understand. What happened to liquid becoming vapor? So its internal energy does not change? That's why I came to this class. This is the last part of your chapter 7. You answer this, we'll split. Afterwards, there's nothing in that. There's nothing. Good question. Everybody understand the question? Yeah? You cannot put CVDT and simply, I mean, nobody will question you, but that is not a full explanation. So you remember, no, it has nothing to do with CV also will change. CV also will change. CV of liquid is more than CV of solid. CV of gas is more than CV of liquid. You remember you said something in that class? Here, watch this. You said that, one second, you will have a certain U only if the entire Q is not converted to. Here you assume that all the Q is converted to what? So it's not becoming liquid is not becoming vapor and getting accumulated there. What is happening is liquid is becoming vapor and it's expanding and doing work. So if it sat in a container, then U should change. But here it's not, it's doing work, it's a continuous process, yes? So all that energy that it is gaining is getting used up for doing work. So the U will not change, got it? So he himself had answered that day. You are supposed to recollect it, okay? Thank you. So all the Q got converted to W. So you are left with no change in U. Get it? If you had collected it in a geyser, then you would have changed the U of water. Cold water to, sorry, there the temperature is changing. Yeah, there it's not isothermal. because you're not making vapor there. You're just using the same liquid to cold. But if water became a vapor, so in a kettle, tea kettle, so temperature will clear. The temperature does not change because all that energy is being used for phase transitioning from liquid state to vapor state. But at the same time, they are also expanding and doing work. So all the Q is getting converted to W. So can you write a relation, because now U is 0. Can you write Q? So what should I label Q as? QH at the hot location. QH is equal to W. Write it in terms of V, because now you know V1 is changing to V2. So what is the temperature? RTH ln V2 by V1. Ln V2 by V1. It's endothermic, right? Q is positive. Q is positive. QH is equal to RTH ln V2 by V1. So I'll go to the next page. So in the isothermal expansion, what happened? U is 0. Can you write now? 1.1. Isothermal expansion. So dt is 0. So du is 0. du is cv dt. W is pdv. Write it one time quickly. Come on. Fast, fast, fast. Too slow, man. Iso expansion. So isothermal expansion. So dt is 0. du is 0, which is cv dt. Work is pdv. Volume changes from V1 to V2. So what is W? RTH ln V2 by V1. That is equal to heat that is being supplied, QH. That's it. So it's a reverse of this is isothermal condensation. Clear? Don't trip over signs. Endothermic is positive, exothermic is negative. Work being done by the system on the surroundings is positive, the reverse of it is negative. Okay, go to the next step, adiabatic expansion. So in the same first law, Q is 0. So what do you have? du plus dw equals 0. du plus dou w equals 0. So second step, adiabatic expansion. Q is 0. Q is 0. So what did you get? du plus dou w equals 0. What is du? Cv dt. What is dt? What is dt? It will cool off, correct? It will cool off. When it cools off, internal energy will increase or decrease? Decrease. So it is TL minus TH. So nothing to get trippy about this. Yeah? CV TL minus TH. Plus work, you're going from V2 to V3. So R, what you will do for T now? What you will do for T? What will you do for T? No, adiabatic I already put Q equals 0. You can use that. P1, V1, use it. You have to use the adiabatic work because temperature is changing during adiabatic work. It is going from hot to cold. Wait, don't run away. Let those guys come, it's fine. So let's see, your first expression is correct. RTH ln V2 by V1, correct? QH. Second one, can you still write with T? Can you still write with T? you should still be able to write with T. Can I equate this to, for dou W, what should I write? What should I write? RT ln V, correct? So can I divide by T? Can I divide by T? Can I divide by T? And so what will I get here? CV ln T is equal to R ln. So what is my volume going from? V2 to V3. So is it by V3 by V2? Is it ln V3 by V2? Write it down, write the adiabatic expansion one time. So your correct expression is yes. So it's R ln V3 by V2. Yeah, that is correct. Get rid of T. Put the T on the other side, on your CV side. CV dt. Just careful when you're doing the integration on the temperature. What is your temperature? You're going from TH to TL. So you will write CV ln TL divided by TH. Got it? Here the integration is from TH to TL. Don't make mistakes with the signs. In the expansion, you are going from hot temperature to cold temperature. Obviously, internal energy will go down. You will get a negative Q. It is giving out heat. Correct? It is giving out heat. Sorry, it's adiabatic. It's not giving out heat. It's just becoming colder. The temperature is changing. It's just becoming colder. So in the first step, V should increase and Q should be endothermic. In the second step, temperature should decrease and your U should decrease and the work is positive. In the third step, work is negative and Q is exothermic because a vapor is becoming liquid. Heat will come out. Exothermic. Fourth step, the work is still negative and the internal energy increases because the heat will increase in the compressor, correct? You're going from TL to TH. Get the loop correctly. In the 1 to 2, there is no change in temperature. In 2 to 3, there is change in temperature, cooling. 3 to 4, no change in temperature. 4 to 1, it's getting heated up again. One is a iso, one is a adiabatic. Iso, adia, iso, adia. That's your cycle. 2 expansions, 2 compressions. And whenever you have iso, there is no change in free internal energy. And whenever you have adiabatic, Q is 0. Clear? Careful with the sign. One more time, I'm going to repeat, endo is positive, exo is negative when it comes to Q. When it comes to W, if system does work, positive. The surrounding does work, negative. Like I said, in the parenthesis you write, okay, whatever sign you get, don't worry about, but make sure your number is correct when you do the arithmetic. Afterwards, you don't have to write it in plus and minus. You write the absolute value and you say work is being done by the surroundings on the system and underline your number with the units. But your obviously signs should be correct when you're doing the arithmetic. Any questions? Oh, hey, it's 10:55. What happened to the clock, man? Okay, I'll catch you Tuesday. Excuse. Take off. Chapter 8. Oh, by the way, 1 second. Some guys put up some questions on imparters. No problem. The best way to answer those questions is you can come to my office or I will take some time out after I come back and answer the questions. But still, I would like to answer the questions in the class. So I'll gather all your questions and come back one time, one class, and answer it here. How about that? Is that good?